Well, I'll get started here. So we're still talking about ring homomorphisms, and we'll be soon talking about, let's see here, I'll say prime subfield, field of fractions, that's where we're going. Hopefully we'll start talking about polynomials today, if I do things right. All right, so first of all, theorem 4.4.10, it says if R is ring with unity 1, then the mapping phi from Z to R defined by phi of n equals n times 1 is a ring homomorphism.
What are we defining unity 1 as? Is that just an identity element?
It's the multiplicative identity of the ring.
Okay.
So multiplicative identity we also call unity. So the to go through the details of this proof, it would be rather involved. But essentially, to prove that this is a ring homomorphism, we need what? We need phi of like m plus n equals to phi of m plus phi of n, right? And we need that phi of mn is phi of m times phi of n. And we need that phi of 1 is equal to 1, right? So those conditions, if you translate them into the definition for phi given here, are really just what? Like m plus n times 1 is equal to m times 1 plus n times 1. And you can prove that. Here, n times 1, what that means is 1 added to itself n-fold times. Right, like n times 1, what that means is 1 plus 1 n times, you know. And you could define that more precisely like by a recursive definition, but I don't want to get into all that. And likewise here, mn times 1, well, that's equal to m times 1 and n times 1. And you can also prove that. And phi of 1, well, that's easier, you know. Phi of 1 is 1 times 1, which by definition is 1. Add 1 to itself one time, you get 1, so yay. Right. Notice the difference, though. Don't be deceived. The 1 in the one entering into the phi is the 1 in the ring. Could be a matrix, could be a polynomial, could be all kinds of things. The 1 that it outputs is the integer 1. I'm just using 1 for both of those, you know, so be wary of the notation. Okay, so there we go. As I mentioned in my notes here, you can find an explicit proof given in Galen's, modern algebra book. Corollary to this, what is the corollary? Corollary 4.4.11 says if our ring and the characteristic of R is greater than 0, right? Well, let's say equals n. Greater than 0. Then R contains subring. All right. Isomorphic. to Z mod n, and likewise, if the characteristic of the ring is 0, then R contains subring isomorphic to the integers. All right, so here's the proof. If you're wondering what characteristic is if the characteristic is n, that means that n, if we add anything in the ring to itself n-fold times, we get 0. And we saw that that's equivalent to the condition that n is the number of times you add 1 to itself and get 0 if it's characteristic n. Characteristic 0 means it doesn't matter how many times you add 1 to itself, you never get 0. All right. Z mod n has characteristic n. Z has characteristic 0. The integers have characteristic 0. Anyway, so the proof here, he says construct this set S, which is k times, so it's multiples of 1.
For example, the characteristic really fast, Z mod 4 is n that equals 4, because that's how many times you got to add 1 to itself to get back 0, but just Z never.
Right. Characteristic 0, right. So if you look at that, and you look at theorem 4.10, what is that? Well, that's the image, right? This is exactly phi of Z for phi of n equal to, n times 1, right? This is the image of that map, right? It's the range of the homomorphism from theorem 4.4.10, right? And what's the kernel of the homomorphism? It is k in the integers such that what? Such that k times 1 equals to 0, right? By definition of kernel. So what is that? Well, that depends on which case we're in, right? If we're in characteristic n, what is it? What goes on here? Which k are included here? If we're in characteristic n, which k are included? Well, multiples of n, right? So this is equal to nz if the characteristic of R equals to n, and it's equal to, it's equal to nothing, right? It's equal to the set containing 0 if the characteristic of R is 0, right? Because the only way you can get something 1 added to itself to get 0 is when you add it to itself 0 times in characteristic 0, right? But what does the first isomorphism theorem say? Remember, the first isomorphism theorem says that the domain of phi, which is Z, mod the kernel of phi is isomorphic to phi of Z, right? First isomorphism theorem for rings. And so there are two cases, right? So if the characteristic of R is equal to n, then Z mod the kernel of phi is isomorphic to what? Well, excuse me, kernel of phi is what in that case? It's nz, right? That's isomorphic to S, right? And that's a subset set of the ring. So this set S that we're constructing is the ring, the subring, which is isomorphic to NZ. I mean Z mod N. See, because this is Zn, right? Likewise, if the characteristic of R is 0, then Z mod the set containing 0 is isomorphic to S, right? Which again is a subset of R. But the thing is, Z mod 0, right? Any ring, if you take, this is a theorem, which I have not proved, but it's easy to prove. R mod the ideal containing just 0 is isomorphic to R again. So like Z mod 0 is Z again. Taking the factor ring formed by modding by 0 is really obnoxious because formally speaking, all it's doing is just wrapping every element in the curly brackets. The equivalence classes are singletons. Yeah, singleton sets.
So it's a power set?
Technically, yeah, it's a power set. But like when you mod by 0, you're just saying, well, the new 0 is 0. But it's 0 for equivalence classes. So equivalence classes are sets of elements, not the elements themselves. So I mean, technically speaking, they're not the literally same object, but in terms of algebra, R mod 0 is R. All right. Okay, enough about that. So that's the corollary 4.12. 11 rather. Corollary 4.12 says that if you look at the mapping phi from Z to Zm given by phi of x equal to x sub m, which of course you could also write as x plus mz, right? Is a ring homomorphism. Now, we already know this, actually. I've told you this before.
Yeah, this is for the polynomial group.
Yeah. But I suppose the point of this corollary is to say, hey, by the way, this ring isomorphism is also an example of the construction of theorem 4.4.10. That's all it's saying. Because basically, the key element, the observation is just this, which is the equivalence class. The representative x is x times the equivalence class containing 1. So it is that construction again. Just to make this a little bit less weird, like if you had, 3 in mod 7, well, that's the same as 3 times 1, 7, right? It is 1 mod 7 plus 1 mod 7. I'm starting to really regret this notation at the moment. 1 mod 7. Aren't you glad we don't always use the bracket sub-residue notation? It's really quite cumbersome for calculation, isn't it? All right. Corollary 13. This is a theorem due to Steinitz. (1910), and it says if F is field of characteristic P, then F contains subfield isomorphic to ZP. Likewise, if f is field of characteristic 0, then f contains subfield isomorphic to the rational numbers. Oh, hey, thanks. I'll take it. It all comes back to me eventually. Thank you. Let's see here. Well, yeah. Okay, so this is pretty neat. So if you have a field with characteristic P, that means you can construct a subfield which is like ZP. If you have a field of characteristic 0, you can construct a subfield which is like the rational numbers. And basically the construction is essentially just this. Let's see here. And this is the characteristic 0 case. Excuse me. So you do, let's say, S sub q. It's A, B inverse such that A and B are in S with B not equal to 0. Now, what is this S we're referring to here? This is the S that we built back here in the proof of corollary 4.11. It's the multiples of 1 right here. How to say it? K times 1. K is an integer, right? So this is a subset of the ring. And the same goes for if you want the sub in the characteristic P case, you construct, let's say, SZP. It's A, B inverse such that A and B are in S. Same deal again, all right? And you can prove that those sets that I just wrote down there are isomorphic to Q and to Z mod P. I think you can even, this is a corollary, so there's probably a slicker proof than the one I'm thinking of. But anyway, I'm not particularly interested in the proof of this. I just want you to know about it, okay? I'm not saying the proof is hard. I'm just saying I want to go on, okay? And really, the key point here is the definition that this allows us to make, which is given field F, all right, the subfield, all right, contained in all other subfields of F is called its prime subfield. I say, and what I point out is from Steinnitz's theorem, right above there, you can argue that up to isomorphism, the prime subfield must either be Z mod P or the rational numbers. Because whatever your field is, you can just take the number 1 in the field and add it to itself a bunch of times to sort of create the integers of the field. All right? And then since you're in a field, you can look at the reciprocals of those, right? Because every non-zero element in a field has an inverse, and that constructs a field inside the field that you're looking at. right? Any other field that you were to construct, any other subfield that you were to construct, it has to have 1 in it. And then once you have 1 in it, you can automatically build this S sub Q or S sub ZP, depending on which characteristic you're in. So that means that the subfield ZP or Q is automatically contained in every other possible subfield. Because once you have 1, you can build either that or that. It's inescapable. All right. So that brings us to the main event for the moment, which is the field of fractions. So let us get to it. So what I'm about to show you is how we can take I think we need an integral domain. And if you have an integral domain, you can build from that integral domain, right, what's called field of fractions, which is, like it sounds, a field. So here's the theorem. Let D be an integral domain. What's that mean? Then there exists a field F that contains subring isomorphic to D. And we call that field the field of fractions. So what did it mean for it to be an integral domain?
Integral domain abelian.
Abelian. I mean, that's the right idea. Commutative, yeah. Commutative ring with identity, right? And no zero divisors. That's a big one. No zero divisors, right? Okay. So let me just kind of show you the man behind the curtain for this whole proof before we get into it. So you guys know rational numbers, right? So what we're trying to do is formalize the construction of rational numbers in some sense here. So A over B is equal to C over D if and only if what? AD is equal to BC, right? So we don't want to write fractions for the proof, because that kind of, it gives you the sense that you're assuming what you're trying to prove. And so I think it's just a good point of sort of, rite of passage, if you like. I just think it's helpful for us to convince ourselves that we're not actually assuming what we're trying to prove here if we use a notation which isn't just the fraction notation. So what we're going to do is, instead of writing A over B, we're going to write A comma B, right? And we're going to say A comma B is equivalent to C comma D if and only if what? Well, AD is equal to BC. So we're going to use A comma B as a temporary, for the purpose of making this proof careful, notation for the fraction A over B.
So are we labeling a map then? That takes are we defining A comma B as a mapping that takes
So,
a ring to something that A over B is?
well, I guess I should, no, I'm not saying, so let me be explicit here. So I'll start the proof here. How about that? Let S equal A comma B such that A and B are in D, right? And D doesn't have to be real numbers, it doesn't have to be complex numbers. It's just an integral domain, okay? And but we do we do want b not to be 0, right? Okay. So if you like, this is our set of formal fractions. You could think of it that way. This is a set of formal fractions. And then we're going to define a comma b is equivalent to c comma d if and only if what? If and only if a d is equal to bc, right? So the first order of business in this proof is to prove that that is in fact an equivalence relation. All right? Because this field of fractions we're constructing, it's actually going to be a set of equivalence classes. Okay, so let's see here. How about reflexive? Is a comma b equivalent to a comma b? That's true because a times b is equal to b times a, right? We're not trying to prove it's, we're trying to prove this is an equivalence relation because we're going to work, because we're going to define operations on the equivalence classes. The equivalence classes of these things are going to be the actual fractions. Yeah, transitive, that's a good question. I'll do symmetric, I'm going to be lazy. So a comma b equivalent to c comma d, that means that, of course, AD is equal to BC, right? And that also means what? Yeah, DA is equal to CB, which is what we need in order for, let's see here. A is playing the role of D, so D, I'm an idiot. That better be CD. Called AB, I have to think through it. I think it's sillier than that. I think it's I think it's sillier than this. I think it's just switching the order in some sense. Like, I'm sorry, just a second here. Let me just. I'm having a crisis of explanation. Let me just try to meet in the middle instead. So if we do the other way around, right? CD equivalent to AB, same pattern, right? So we do first times last, and middle times first, last and the first times the first and the second. Whatever you want to say for the language here, DA anyway. And of course, these equations are interchangeable, which proves symmetric. Transitive. Transitive. I'll use E and F for the last one here. So this gives you AD equal to BC, right? This one gives you CF equals to DE. But what do you want? You want these to imply AB equivalent to EF, right? So to get that, I need that AF is BE, right?
equivalent to saying AEBF, right? And you could set A in for stuff and things would drop out.
Yeah, it's something like that. Let's see, consider ADF equals to what? I mean, that's, of course, that's equal to, let me not play around here. We could easily eat up 10 minutes on this. It's not that interesting. I'll copy my notes down because I think this is one of those things that's easy to kind of get lost. I can trade AD for BC, right? First condition. But I can also, by associativity, rewrite this as B times CF, right? Using the associativity of the ring multiplication. But then, of course, CF we can trade for DE, right? But of course, we're in an integral domain, right? Commutative. So that means I can rewrite this all together as, let's say, AF times D is equal to BE times D, right? Now, AF equals to BE is what I want. And why do I get it? See, why does this imply AF equals to BE? Thus establishing transitive.
So AF. Okay, let's go through your steps. AD is equal to F if BC's, or yeah, ADF is equal to BCF. But we know that AB is equal to BC. So we set that in. We have B equal to DE. Cool. And CF is equal to, so we need, what do we need? We need AF. I'm looking for math. So BC divided by D is F, and BE is AF.
I can't divide. I don't know
Oh, yeah, we
anything.
can't divide.
I don't know anything here has is a unit.
Um,
I know that. So if this is equal to that using commutative,
Yeah.
I just factored D out this way and that way. The reason I did that, we're in an integral domain. We have cancellation property. So since this is equal to that, cancellation property, right? It implies that AF is equal to BE, which is so transitive. That's why we need integral domain. And we haven't used that up until now, but now we've used it. Okay? So the fact that integral domain is necessary to get the transitive property. All right, so there we have it. This equivalence relation is indeed an equivalence relation. Okay? And so continuing here, let us, can I erase?
Oh, let me,
You're fine. You know what I'll do? I'll just write it up here.
nope, I'm good.
So our claim is that S mod tilde, which is what? This is the set of equivalence classes, right? So this is like so A comma B such that AB is in S. Here, A comma B with a closed bracket, it's equal to C comma D such that AB is equivalent to CD. So with the square bracket, it's the equivalence class. The equivalence class of all similar pairs in S, okay? And S mod tilde is the set of equivalence classes. All right, so it's a set of sets. So it's on this S mod tilde, if you like, that we're going to hope to, our hope is that this S, by tilde is the f that we want to construct. Like, essentially, our goal is, let me call this thing f, all right? So how are we going to, so for f to be field, what do we need to define for it? We get it to be a ring, right? Which means we need to, so again, the man behind the curtain, right? If you have A over B plus C over D, how do you define that to be? And how about A over B times C over D? How do you do that? Well, we know that. That's AC over BD, right? And cross multiply, right? Like AD plus BC over BD, right? So since we know that we know that from our, childhood work on fractions, so that instructs us that this formal construction should mirror these things, right? And so what we're going to say is that if you add the equivalence class A comma B to the equivalence class C comma D, the way to do that is to get the equivalence class AD plus BC comma BD, right? This is, again, a thing of the right form, right? B and D are non-zero, therefore BD is non-zero. That's a good sign. And how do you multiply these equivalence classes? That's a little bit easier. You just multiply the first and the second components, respectively. So these, what I just wrote in red, these are definitions. Now, this is for what? This is for we're defining this for A comma B, C comma D, and F, right? But here, what is F? F is a set of equivalence classes. So anytime you make a definition for a set, right, where the label of the elements are not unique, you have to check that your rule is not dependent on that labeling, right? We have to check that these operations are well defined. So how's that go? Well, so if you have A comma B equal to, say, A prime comma B prime, right, and C comma D equal to C prime comma D prime. So we have two different choices of representative. What would we like to show? We'd like to show that, A prime comma B prime plus C prime comma D prime. Well, what is that? Well, by definition, that is A prime D prime plus B prime C prime comma B prime D prime, right? So we're like, assume, these guys right here, right? Now, so I'm just continuing over here. Sorry about my organization, not the greatest, but this means what? This means that AB prime, right, is equal to what? BA prime, right? This? No, these are I'm referring to elements in the D, and also CD prime is equal to DC prime. I think I'm missing. Yeah, we're going to, again, I think, need to use the, well, anyway, I better, okay, so, all right, so let me get straight to the point here. We'd like for this to be equal to what? A comma B plus C comma D, right? That's what we're trying to show. We're trying to show that you get the same outcome no matter which representative you use, right? And so, of course, this is what? This is AD plus BC comma BD, right? So what we need to prove, right? Our goal at the moment is to prove the thing with the primes and the things without the primes are equal. We need to show that these are equivalent, right? What does it take to show those are equivalent? It suffices to show that A prime D prime plus B prime C prime times what? Times BD, right? Is equal to what? See, that's this times that. It's supposed to be equal to that times this, right?
Yes.
So if we can prove what I just wrote in black is a consequence of our assumptions, we need to show somehow that these guys right here give us that down there, right? That's our goal at the moment.
So, well, we have transitivity, right? So that gives us, what we got now.
Tell you what I'm going to do. No, I'm going to write down the equation in my notes and see if we could come to terms with why I wrote it. Sound good? Let's do that. This is one of those proofs where I need about 2 more boards to do it properly. Like I'm suffering from lack of board space in here a bit, especially not usually, but this proof in particular, yes, because I'd like to make everything big and keep everything out, but I just can't, you know. Anyway, so I say consider then, I got to be careful, make sure I use the same letters before I get carried away here, huh? All right, so I say consider, I take AD plus BC times B prime D prime, and I say that that's equal to A B prime times DD prime plus CD prime times BB prime. So that's just distributing. Nothing yet there happened. And then what do? I trade my AB prime for my BA prime, all right? And DD prime stays put. And I'm going to trade that for, I think, a DC prime. So see, I just used both. I used both of the assumptions in that step. So that you know, let me call this thing star. So this is by star. And so factor out BD, what you got? You got A prime, D prime, plus what? Looks like B prime, C prime, yeah? What are we trying to prove?
That is equal to that.
Oh, hey, that's what we're trying to prove. Hooray. So it's actually not bad. You just have to like find a way to make use of what you're doing. And it really, yeah, I literally just started with, I literally just started with this here. And got over to this one. So it's just that. And so therefore, addition is well defined on S mod tilde, right? Now we should check that multiplication is well defined, right? So what we want to do is, again, we're going to assume we'll still use the same notation, right? Same notation. So we want to check that A, B, A comma B, C comma D is equal to A prime comma B prime, C prime comma D prime. All right. And so that is what? So this is A C B D equal to A prime, C prime, B prime, D prime, right? And to be clear, I'm asking a question here. I don't want to say that that's automatically equal. That's not really what I'm, like, this is the question, right? This was always a question. Is that equal? You know? It drives me nuts with you guys. When you write proofs and you write what you're trying to prove in the middle of the proof. And I'm kind of doing the same thing here, which is a very bad practice, you know? The question is, are those equal, right? Okay, so this being equals to that is equivalent to what? Yep.
Prime D prime equal to BD A prime C prime.
Right. So consider AC B prime D prime, right, is equal to AB prime times CD prime, which is equal to BA prime times DC prime, right? Which, by the way, is equal to BD times A prime C prime. So there you go. That proves it. Thus, multiplication is independent of the coset representative. All right, so therefore, multiplication well-defined on the set of equivalence classes. Now, I say well-defined, all we've done at the moment is show that they're functions, right? That they're binary operations. I haven't really even shown that entirely, but it's clear from their definition that they're into, like they're actually mapping back into the set of equivalence classes. We still need to prove that the addition and multiplication satisfy the field axioms, right? Yeah. So what are some things we should pick on in there? We will not have time to do all of them, but I'll just try to hit some high points here. How about 0? What is 0 in F? Yeah, what is 0? How about this? The 0 is played by the equivalence class of 0, comma B.
Okay.
Now, if you don't like B, I could put a 1 there just to make it specific.
No, we're talking about an AB representative, ABCD representatives B.
So you doubt me. All right, so 0 plus A comma B, right? That's 0, comma 1 plus A comma B, yeah? By definition, that is, what is it?
0A
Mm-hmm.
equals B.
0A, 0 times A plus 1 times B, right? Excuse me, 0 times, you tricked me. I was tricked. 0 times B plus 1 times A, and then BD, right? So 1 times B. That's that's AB. So 0 plus AB gives you AB again. That means my 0 is a 0, because you can also prove that the addition is commutative. That does sound like a homework exercise, doesn't it? Homework. So addition is commutative. What is 1? What is 1 in this field? But yeah, it's the unity. But what is the 1 in the field we're building? It's played by what?
Something that is multiplicative inverse, or that if you multiply by multiplicative inverse, gives you back it's 1, gives you back the identity. Am I confused on the question?
No. Let me here. Let me pose a question to you a different way. Remember, a over b is like our a comma b, right? So if you wanted a over b to be the number 1, what would you choose a and b to be? Equal, right? How about? But we need to make it specific. So thing we got to work with for sure is 1. So 1, 1. And you can try it out. Try it on for size, right? So like 1 comma 1 multiplied by a comma b, what's that equal to? 1 times a comma 1 times b, that's ab again, right? So that shows you that the equivalence class generated by 1 comma 1, hey, that's serving as the multiplicative identity in this field of fractions we're building. Does that make sense? So you can prove that addition is commutative. You can prove that it satisfies the distributive property with respect to the addition and multiplication. I think at least some of those, maybe all of those are in my notes. So if I assign these as homework, it's very generous, right? The other thing I'd like to look at here before we go past this proof, how about it's a field, right? What does that mean how do you know it's a field?
That satisfies the axiom.
Yeah, but what's the main thing that makes a field different than other, like an integral domain or other things? What makes a field a field?
It's complete. There's no holes.
There's no holes. Well, they can have holes. Like Z mod P's got lots of holes.
Okay. Think about things. Oh, no, we already got that.
Every non-zero element
One can build the entire set.
is well, that's not necessarily the case either, as I'll show you in a minute.
Like the unit can build itself.
How about this? Every non-zero element has a multiplicative inverse, right? That's what a field is.
Okay.
So every non-zero element is a unit. So if this F that we're building is a field, we need to be able to exhibit the inverse for an arbitrary non-zero element, right? So let a comma b not equal to 0, right? Note, by the way, that 0, 1 is equivalent to 0b, okay, for what it's worth. So, I mean, in other words, to rule out 0, we just assume the first entry is non-zero. So we consider a comma b such that a and b are both not 0. Okay? That makes it a non-zero formal fraction. What do you think the inverse is? What is the inverse to a comma b?
Well, it would have to get you 1 back, so I would say A inverse, comma B inverse.
But we don't know that a inverse and b inverse exist. The whole point of this construction is that they might not.
Would it be, okay, wait, is it 1 comma A, 1 comma B?
No. Let me put it in other terms. So if you had a over b, right?
That would be A.
You might, yeah, ba.
I was going to get there eventually.
Yeah, I thought so.
Should just kick me around.
So the question is, why is that? The claim is that that's equal to 1.
Yes.
in the field of fractions. How do we show that?
Is it sufficient enough to say that given any choice,
Let's see here.
AB,
Well, this is by definition. This is what? This is AB, comma BA, right?
is it sufficient enough to say that given any choice of A and B, they'll always be related to 1, 1?
Yeah. Well, well, let's see. The question is, can we show this? I want to say this is true since AB, comma BA is equivalent to 1, 1, which is true since what?
Oh, we could show the transitive property.
Yeah, AB times 1, right, is equal to BA times 1.
Can we use the transitive property? No.
Uh,
Yeah, I think you could.
Well, I have to use the
AB,
I mean, commutative property down here, I suppose, and maybe associativity, but anyway, this shows you that indeed AB inverse is equal to BA. Woo. You can prove more here too, by the way, like here's a lemma. So like AB is equal to, say, AC comma BC for C not equal to 0. You could prove that as well. All right, so again, so I haven't proved everything, but do you see how you'd go about proving the other properties? Like, so I will make a homework on some of the things we haven't done, and again, those are partly contained in my notes. Like I have proof. I think I may have proofs of all the properties actually on page 141. I probably should just do them. I will resist, though. So the point is, put this all together, complete the thought. What do we have? We have, from an integral domain, constructed a new set F, right, where every non-zero thing has a multiplicative inverse. It has a commutative addition, a multiplication, which is distributive across addition as we like. And so this is the so-called field of fractions. And of course, you know, for the sake of future reference, I'll write it over here. And so we, definition, we'll just say A comma B is equal to A over B. All right, thus F equal to A over B such that, you know, A and B are in the integral domain D with B not equal to 0 is the field of fractions. For D. And what's the subring? How does this contain D as an isomorphic subring? Like what is that? How do you get back D inside this thing?